Hey guys, welcome to A2. I'm sorry I can't be with you today, but we're going to go ahead and try this out. So last class we were going to start 10.2, but we decided to keep going on some of the stuff from Chapter 9 so you'd be ready for your test. So this is going to be fast and furious graphing quadratic functions. Now there's always one surefire way to graph a quadratic function, and that would be to plug in points. Okay? When in doubt, plug in points. If I give you a function x squared plus 3x plus 1 and I say graph it and you are completely lost, then plug in points. You just pick some, okay? And eventually you'll get a graph that looks like something. But I'm going to give you a way that actually will give you a step-by-step instructions on how to graph it the most efficient way possible. So, we've spent the better part of a semester learning how to factor, solve, and manipulate quadratic equations. But what do they actually look like? Back in the day, which was third quarter, we looked at basic graphs of several functions. We looked at lines, we looked at parabolas, and we also looked at cubics, and we looked at square roots, I think. And we looked at cube roots. Yep, we did. The one we're going to focus on for the time being is called the quadratic function, which takes the shape of a parabola. Okay, and it looks like this, generally speaking. Okay? This is the graph of the quadratic function. Okay, f of x equals x squared. That's what the function's equation is for this. All right? The line here, if you can imagine, I mean, it's not always the y-axis that does this to the quadratic equations, but for the parent function it is. And this is called the axis of symmetry. As you can see, if I folded this piece of paper in half, I would actually get the same thing on both sides, and that it's symmetrical about the y-axis. This specific one is, okay? The domain of all quadratic functions is all real numbers. Okay, so that would be negative infinity to infinity is the domain. The range depends on the vertex and the concavity of the graph. And what I mean by concavity is it pointing up or is it pointing down? Okay, this is the vertex. That's the lowest point, or in this instance, the highest point. Okay. And it's called, this is the vertex right there, we're going to label it. And this is a very important point, it's where it turns around, okay? And notice it lies on the axis of symmetry, very important. A function that can be written in the form f of x equals ax squared plus bx plus c for real numbers a, b, and c with a not equal to 0 is called a quadratic function. Okay, so it has to be able to be written in this form. Now b can be 0 and c can be 0, but a has to be some number other than 0 in order for it to have this shape. However, the standard form ax squared plus bx plus c is not the best way to graph a quadratic function. It's easier to see how to graph a function in terms of transformations of the parent function. So first we're going to graph the parent function because that's the most important one for us to have in order to graph transformations. So I'm going to graph when x equals 0, the parent function is f of x equals x squared. That would be 0 squared, which is 0, so I'm going to plot this point. When x is 1, 1 squared is 1, so that would be this point. When x is 2, that would be 4, so 2 4s right here. 3 9 would be another point, which is right here. And if I plugged in negative, all of the negatives of these values, I would get the positive version of those squares. So that would be negative 2 would be positive 4, and negative 3 would be positive 9, etc. So I'm just going to go ahead and graph those. And then you connect the dots in a nice smooth curve. Now as you can see from my graph, I have an axis of symmetry that's right here. My vertex at this point is at 0, 0, the origin, and you can see that I go over 1, up 1, over 2, up 4, over 3, up 9. Those are normal squares. Okay, well, the first type of transformation we're going to look at is the vertical shift. If you add a number to the parent function, f of x equals x squared, to make it f of x equals x squared plus a, or we'll call it plus c. Then you have translated the graph c units up or down. Okay? So, for example, graph f of x equals x squared plus 3. So 3 is my shift, and I'm going up. So my transformation is a vertical shift up 3. Okay? So instead of having, and that's all I'm doing, so instead of graphing the parent function starting at the origin of 0, I'm going to shift every point up 3 spots. So now my vertex, instead of being at the origin, is at, my vertex is at 0, 3. Now all of my other ones are just shifted up 3 spots as well. My 1, 1 is now here and here, and then over 2 up 4, 1, 2, 3, 4, and the other one was over 2 up 4, and this one was over 3 up 9, but I don't have any more space for that, so I'm just going to graph this. And we've graphed it. Now the domain is the same. The domain is always going to be negative infinity to infinity, but my range has changed. Originally, for the parent function, my range is 0 to positive infinity. But here, my range is 3 to positive infinity because I shifted it up 3 units. So I can start at 3 and I go to positive infinity. Okay? Well, let's graph this one. So here we have a vertical shift of down 5 units because my C is negative and it's going, negatives numbers go down. So we're going to go down 5 units, 1, 2, 3, 4, 5. That's my new vertex because that's the only shift or transformation that I have here. So let's see, that's going to be a vertex of 0, negative 5, over 1, up 1, over 1, up 1, over 2, up 4, and there, and over 3, up 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I go over 4, how many will I go up? Well, if you said 16, you would be right. That's 9, 10, 11, 12, 13, 14, 15. 16 is way up here, but I just wanted to make that as a point. All right, just for your knowledge purposes. Okay, and I'm going to graph this parabola, and there we go. The domain is going to be all real numbers again. And the range, I bet you can guess it, would be negative and 5 to infinity. And include negative 5. Okay? All right, so horizontal shifts. If you add a number to the x value of the parent function, f of x equals x squared, to make it f of x equals x plus h squared, well, here, let me, x minus h, we'll do it that way, x minus h squared. You have translated the graph h units to the left or to the right. Now, we need to talk about this because if it's x minus h, okay, then this would be x minus negative 2 squared, okay, which means it's going to the left, okay. So you have to make sure that it's kind of like it's the opposite of what you would think. This is not 2 units to the right, this is 2 units to the left. So we're going to go 2 units to the left, and that's the only transformation. So my origin, my vertex, is now going to be here, and I'm going to go over 1, up 1, over 2, up 4, over 3, up 9, 5, 6, 7, 8, 9. And the axis of symmetry has shifted as well. Notice my axis of symmetry is no longer the vertex, is no longer the y-axis. It's the line x equals negative 2. So that is helpful when I'm graphing my points here. And there we are. There's my graph. My vertex is negative 2, 0 now. My domain has not changed. Negative infinity to infinity, and my range is now the lowest point is at 0, so it's still 0 to infinity. So there we go. Horizontal changes don't change the domain and range. So here we go again. Let's try this one. This time I have x minus positive 3 squared. So this is a shift to the right 3 units. And that's it. So my vertex has shifted from 0 to 3. I'm going to go over 1, up 1. My axis of symmetry is now here at x equals 3. Oops, I missed that point. And then I'm going to go over 2, up 4, over 2, up 4, over 3, up 9. All right? And then I'm going to graph this curve. Okay, the vertex is now 3, 0. My domain has not changed, negative infinity to infinity. There we go. And my range is now going to be 0 to infinity. It didn't change at all because I didn't shift it up or down. The y value is the same. Okay, so that's the set of notes for Chapter 10.10-2, Part 1. So if you need to refresh, this is where you can pause, rewind, finish the notes, understand the vertical shift and the horizontal shift. Those are both very important parts, and the next part is a little bit trickier. All right, so let's move on. Here's the second part of the notes. If you multiply the parent function f of x equals x squared by a to make it f of x equals ax squared, then you have stretched the graph vertically. Okay, so we're going to look at it. Normally, the parent function looks like this. But if I have a vertical stretch, it makes it skinnier, so that instead it might look a little more like this, like a little skinnier, right? So here's what we've got. This is the parent function. Okay, notice I have 0, 0. I go over 1, up 1. Okay, I'm going to C, I go over 1, up 1. Okay, this is a 1 and this is a 1. And I go over 2, up 4 to get to D. All right, well, let's look at what happens when I multiply it times 2. Well, I still have 0, 0, but now instead of going over 1, up 1 to C, I go over 1, up 2. And instead of going over 2, up 4 to D, I go over 2, up all the way to 8. So what can we do to help us graph these things? Well, if you notice that my A was 2, all I did was I multiplied 4 times 2 to get 8. I multiplied 1 times 2 to get 2. So the vertical difference, the vertical distance, instead of going over 1, up 1, over 2, up 4, I'm going over 1, up 1 times 2, over 2, up 4 times 2. Okay, and that would be 8. So let's see how that works with this. If prediction-wise, if my A is 1/2, then instead of going over 1, up 1, I would expect to go over 1, up 1/2. And over 2, instead of going up 4, I would go over 2, up 2. Well, let's see if that's the case. Well, to get to C, I can see that it's right at 1/2. And to get to D, it's at 2. So I went over 2, up 2, and over 1, up 1/2. So it cuts my vertical distances by half. This one makes it stretch by a factor of 2. So this is more of a compression, and this is more of a stretch. Notice the fraction makes the parabola look much wider, and the number that's bigger than 1 makes it a lot taller, much more vertically skinny, I guess you could say. So here, it looks like my vertical stretch is a factor of 3. So instead of going over 1, up 1, I'm going to go over 1, up 3. Okay, I multiplied my vertical values by 3. So I didn't do any horizontal or vertical translations, so I'm just going to start at 0, 0. Over 1, instead of going over 1, up 1, I'm going to go over 1, up 3. And I'm going to do that again over here because this is my vertex and my axis of symmetry runs right through my vertex. Over 2, up 4 is now going to be over 2, up 12. Well, this is 10, 11, 12 is about right there. So I'm just going to graph it so I have a way to kind of aim, I guess you could say. And there we go. Now if I superimposed the parent function, 0, 0, over 1 up 1, over 2 up 4, over 3 up 9, you can see that the one that we just graphed is much, much steeper. Okay? We didn't change the vertex at all. The vertex is the same. So it's still 0, 0. My domain is still the same, negative infinity to infinity. And my range is still the same, 0 to infinity. But what has changed is the steepness of my graph. All right, let's look at this one. Well, according to this, I've got a vertical stretch with a factor stretch of a factor of 2/3. So instead of going over 1 up 1, I'm going to go over 1 up 2/3. Okay, and one that might be a little easier to see that with is 3. So over 3, instead of going up 9, I'm going to go over 3 up 1/3 up 2/3 of that, which is 6. Okay, so I've got 0, 0 is the same. Over 1 up 2/3, which is about right there. Over 2, and it was 4, so I'm going to multiply 4 times 2/3, and that's going to give me 8/3, which is 2 1/3. 2 2/3. 2 2/3, which is right here. And then over 3, instead of going up 9, I'm going to go up 6. So this is 1, 2, 3, 4, 5, 6 right there and right there. So it looks kind of like this. It looks a little wider. Okay? My vertex hasn't changed. It's still 0, 0. My domain hasn't changed. It's still negative infinity to infinity. And my range hasn't changed. It's still 0 to infinity. All right, vertical flip. If you multiply the parent function f of x equals x squared by negative 1 to make it f of x equals negative x squared, then you have flipped the graph vertically. Let's see, flipped. Okay, and what I mean by that is now instead of going up like a cup, it's going to go down like a frown. Okay, so the vertical changes are the same. It's just now it's going down instead of up. So here I have a negative, a flip, and a vertical stretch. So this is going to be, my transformation is a vertical stretch of a factor of 2 and a vertical flip. So it's going to go down, and my transformations are the same. Okay, so I'm sorry, I didn't shift it left or right, so it's still 0, 0 for my vertex, and my domain and range are still the same. Oh, but now my range, let's see what the range does, if it does anything. But let's see, we've got a vertical flip, so instead of going over 1, up 1, I'm going to go over 1, down, and how many? I'm going to go down 2, because it's got a stretch. And then over 2, down, instead of going over 2, down 4, I'm going to go over 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8, which is right here. Okay? Oh, look at this. It's no longer from 0 to infinity. It's now from negative infinity to 0 because I'm going down to and up. Okay? All right. If a quadratic function is written in the form f of x equals ax plus ax minus h squared plus k, it's in vertex form. It has the vertex HK, and the vertical line x equals h is the axis of symmetry. The graph opens up if A is positive and down if A is negative. The graph is okay. 5, 4, 3, 2, 1. The graph is steeper than the parent if A is greater than, well, the absolute value of A is greater than 1. The graph is, we'll call it wider than the parent if the absolute value of A is less than 1. And we're talking about a fraction between 0 and 1, but not including 0. Okay. All right. So, let's see what we've got here. Decide whether each parabola opens up, down, and whether it's wider or narrower than the graph of f of x equals x squared. So this is a parent function. We're going to determine whether it goes up or down and whether it's wide or narrow. Okay, well this one looks like it's going to go down, so it's going to down like a frown because it's got a negative, and it's going to be wider because it's 2/3, not bigger than 1, it's less than 1. All right, this one has an A that's positive, so it's going to go up, and it's going to be wider because it's the A is less than 1. This one is going to go down, and it's going to be narrower because it's greater than 1. A is greater than 1. And this one's going to go up and be narrower because A is equal to 3, and that's bigger than 1. All right, so let's see what we have here. We've got one with all the bells and whistles, and we're going to graph f of x equals 1/2 x minus 2 squared plus 1 and give the vertex, the domain, and the range. So let's see what I have here. My vertex has been shifted. We're going right 2, up 1. So I'm going to go right 2, up 1. So there's my vertex. So my vertex is at 2, 1. And I have a vertical stretch of 1/2. So instead of going over 1, up 1, I'm going to go over 1, up 1/2 on both sides. Over 2, up 4 becomes over 2, up 2. Over 3, up 9 becomes over 3, up 4.5. 1, 2, 3, 4.5. And that's as many as I really want to make right now because we're going to get kind of crazy. There we go. All right. So we've got our vertex. Our domain is now the same. It's still the same, negative infinity to infinity. And our range is a little different. Okay, because our range has been shifted up 1 unit. So that means we're going to go from 1 to infinity. Okay, so now let's look at using the calculator to find a quadratic model for the data. Well, if I give you a bit of a data table for you to do stuff on, I want you to know how to do this on your calculator. So first, open a new document in your calculator. So we're going to do that. We're going to say on, new document. We're going to insert a table, okay, and that's a list in a spreadsheet. Then we're going to insert the data into the table and use an x value that would make sense. We can write the variable name up there. So let's just go over here and see what we've got so we can start making our table. You can follow me as I do my stuff on my calculator. The table below lists the number of Americans in thousands who are expected to be over 100 years old for selected years. So years is the independent variable, so that's what I'm going to write. Up in A, above the gray box, I'm going to write year. And the number of thousands of people, okay, who are over 100 years old, I'm going to put the people, okay, for B. We can only use one-word phrases, so yeah, you got to be kind of creative in that situation. So here we go. Instead of using 1994, 1996, 1998, I'm going to use 1 for 1994, or 0 for 1994. I'm going to use 0 for 1994. Come on. 2 for 96, 4 for 98, 6 for 2000, 8 for 2002, and 10 for 2004. I'm going to use years since 2000 because otherwise it's not going to work out nicely in my graph. So let's see. We've got 0, 2, 4, 6, 8, 10. Okay. And the number of thousands of people are 50, 56, 65, 75, 94, 110. Okay, use this data to find a quadratic function that models this situation. So now what we're going to do, once we have the data in the table, we're going to press Control and plus page, so to Control Doc, and then add a data and statistics. Then you're going to click on the bottom where it says click to add variable, and you're going to put the independent variable, which is year. And over here we're going to put the people. Okay, and now what we're going to do is we're going to find a quadratic model for that. We're going to say Menu, Analyze, Regression, and Show Quadratic. And there we go. We found a quadratic model for this data. So go ahead and we can write this down in our information on our notes. And it's going to be kind of hard for me to do that. So I want you to go ahead and write y equals 0.402. We'll round it to 3 decimal places. X squared plus 2.039. X plus 50.071. And then, if this trend continues, how many Americans were over 100 years old in 2008? Okay, so I'm going to see if I can copy this. I don't think I can. I'm going to go ahead and we're going to go to another page, or I'm going to just use this right here. So 0.4 in 2008 is going to be when X is plus 4, 14. So I want to know when X is 14 what this value is. So I'm going to just insert a calculator. Okay, and I'm going to do 0.402 times 14 squared plus 2.039 times 14 plus 50.071. 50.071. Oops, 71. All right, I press enter and I get 157.4 thousand people. So I'm going to put just the whole number because all of these are in its approximations. So approximately 157,000 people. All right, is it people? Okay, so there we go. That's how you would use your calculator, and you've got that in your notes. So now with the rest of the class period, I'd like you to start working on your homework, and you may need to go back and re-watch some more of the videos, some of the video again, just to get it all nailed down. So here you are, and I will see you guys later. Bye.